All right, let's dive into what is, no joke, the single greatest detective story in all of science, the hunt for the dark universe. And this is a case where the crime scene is literally the entire cosmos, and, well, almost all of the evidence is missing. Everything really starts with this one number, 95%. So what is this? Well, this is the amount of our universe that we fundamentally cannot see, we can't touch it, and we can't explain it with our current understanding of physics. I mean, just let that sink in for a second. Everything we know, everything we've ever observed, every star, every galaxy, every planet, you, me, all of it, that makes up just 5% of reality. The other 95%, it's a complete and total mystery. So welcome to what cosmologists call the 95% problem. Now, our best scientific model of the universe, it breaks it all down like this. You see that tiny little 5% sliver there, the one labeled ordinary matter? Yeah, that's us. That's everything we can see. The other two giant slices, dark matter and dark energy, they are the two prime suspects in our cosmic mystery. They completely dominate the universe, and yet we have basically no idea what they actually are. So let's meet our first suspect, dark matter. This is the invisible stuff that seems to be providing all the extra gravitational muscle needed to hold the entire universe together. You see, without it, galaxies as we know them, they would have just flown apart billions of years ago. And you know, the clues for this invisible matter, they've been piling up for almost a century now. It started back in the 1930s, when an astronomer named Fritz Zwicky saw galaxies in a cluster moving way too fast to stay together. But it was in the 70s that Vera Rubin made a truly groundbreaking discovery that really cemented the case. And this is what she found. This is where it gets really weird. See, based on all the visible stuff, all the stars and gas you can see, stars on the very edge of a galaxy should be moving much slower than the stars in the middle. Kind of like how Pluto moves way slower than Mercury in our solar system. But they aren't. They're all moving at pretty much the same crazy high speed. And there is only one way that's possible. If the entire galaxy is sitting inside a massive, invisible halo of matter that's providing all this extra gravity. So we defined dark matter by what it does. It's kind of like the universe's invisible anchor. It's non-baryonic, which is just a fancy way of saying it's not made of the same stuff as us. No protons, no neutrons. It doesn't interact with light at all, which is why we can't see it. But it's gravity. Its gravity is what shapes the entire cosmos. And if you need a smoking gun, a single piece of evidence, look no further than the bullet cluster. This is just brilliant. What you're seeing here are two galaxy clusters that smashed right into each other. Now, the visible matter, all that hot gas, it collided and slowed down right there in the middle. But gravitational lensing shows us that most of the mass, the dark matter, just sailed right on through like a ghost. This pretty much proves dark matter is a real, separate substance. It's not just that we're misunderstanding gravity. Okay, now for our second and, honestly, even more bizarre suspect, dark energy. If dark matter is the anchor holding things together, dark energy is the engine that's pushing everything apart, faster and faster every second. So how on earth did astronomers figure this out? Well, they used a clever tool called a standard candle. Specifically, a certain type of exploding star called a Type 1a supernova. The key is that they always explode with the same actual brightness, so we can tell how far away they are just by seeing how dim they appear. It's like if you know you have a 100-watt light bulb, you can figure out how far away it is just by seeing how faint it looks. And in 1998, two separate teams of astronomers were doing just that. And they made an absolutely shocking discovery. The most distant supernovae they could find were even dimmer than they were supposed to be. And that could only mean one thing. They were farther away than our models predicted. The expansion of the universe isn't slowing down because of gravity, like everyone thought. It's speeding up. This mysterious accelerator is what we call dark energy. It seems to be a property of space itself, a kind of cosmic anti-gravity that's pushing everything apart. And this isn't some minor effect. Dark energy makes up a staggering 68% of everything in the universe. It's the dominant force in the cosmos. Okay, so we've found our two culprits, right? Dark matter and dark energy. Case closed? Not even close. In fact, these so-called solutions have thrown physics into a full-blown crisis, creating puzzles that are even deeper and more profound. This quote, it refers to something called the cosmological constant problem. You see, our best theory of particle physics predicts that even empty space should have some energy, a vacuum energy. The problem? When we calculate how strong that energy should be, our prediction is off from what we actually observe by 120 orders of magnitude. That is a 1 followed by 120 zeros. It is, without any exaggeration, the single biggest disagreement between theory and observation in all of science. It's just catastrophically wrong. And then there's this thing called the Hubble tension. It's a major disagreement over how fast the universe is expanding right now. When we measure the rate using things nearby, like those supernova, we get one number, about 73. But when we look at the light from the very early universe and use our best model to calculate what the rate should be today, we get a totally different, slower number, about 67. And both of these measurements are incredibly precise. This isn't a small error. It's a huge red flag that our standard model of the universe is broken, or at the very least, incomplete. And it's not just the expansion rate. There's another nagging problem in how clumpy matter is across the cosmos. Based on our models, the gravity from all that dark matter should have pulled things together into slightly denser, lumpier clusters of galaxies than what we actually see. It's almost as if the growth of these giant structures has been, well, suppressed somehow. It's another major crack in the foundation of what we think we know. Now you might be wondering, why does all this matter? Well, solving this cosmic mystery isn't just some academic exercise, because the true nature of dark energy, that's what's going to determine the ultimate fate of everything that has ever existed. Depending on exactly what dark energy is, there are a few possible endings for our universe. The Big Freeze seems to be the most likely one, where the expansion just goes on forever until everything is cold, dark, and empty. But if dark energy is something more exotic, something called phantom energy, then we could be headed for a big rip, where the acceleration becomes so violent it literally tears apart galaxies, stars, and even atoms themselves. A big crunch, where everything collapses back in on itself, well, that's looking pretty unlikely these days. But here's the good news. We are not just sitting around guessing. A whole new generation of incredibly powerful telescopes, like the Rubin Observatory and the Euclid Space Telescope, are right now mapping the dark universe with a precision we've never had before. Think of them as our lead detectives on the case, designed specifically to hunt for the clues that could finally crack this thing wide open. And so that leaves us with the ultimate cliffhanger. Will our universe end in an eternal, lonely freeze, or a sudden, violent rip? The answer is out there, hidden in that mysterious 95% of the cosmos that we can't yet see. The clues are being gathered as we speak, and solving this grand cosmic mystery will tell us not only what our universe is made of, but how its final chapter will be written.